Hello, this is video number 7 on honors linear algebra and multivariable calculus. In this video, we're going to go over systems of equations, systems of linear equations, how we solve them, echelon form, reduced echelon form, and how it is related with bases of Rn. So here is an example. I'm going to start from an example and discuss how we can use this idea of linear, idea of elementary row operations to solve systems. And given that, we will talk about in general what to do. So if you are given a linear system of equation, you have two different methods for solving it. So if you have an equation like this, 3x minus 2y equals 15, x plus y equals 7. In high school or perhaps in middle school, you have learned two different methods for solving equations. The first one is substitution, which means you find one of the variables in terms of the others, and you usually start from something that the coefficient is 1 or -1 if there is such a variable, and then you plug it into the other equation and then you solve. If you have two equations, two variables, this method is going to be pretty straightforward. The other method is what we call elimination. And what we do is we multiply one of these, or perhaps two of them, by two numbers, equations by two numbers, and then add them. For example, you multiply this one by 2, and then you get a -2y and a +2y, and then you add them. So if you have more than two variables, similar methods would work. However, the substitution is a little bit more of a headache to keep track of all these different things, and things get very complicated. Elimination is a bit easier if you organize your work a bit more clearly. So how do we organize our work? So really, if you think about this example, I have three equations and three variables, and that's what I'm going to use to illustrate what we do. Instead of writing down the equations, we really care about the coefficients. As long as we know which variable is the first variable, which variable is the second variable, and which variable is the third variable, I can create a matrix called augmented matrix and place all of these coefficients, 3, 2, -1, and the constants, 4 in this case, into that matrix. So 1, 3, -2, and then 1, 5, 1, -1, and then 4. Then I can just work with this matrix. So how do we eliminate? The way we eliminate is we take one of the rows and we subtract a multiple of that row from the other two rows. And that way I can create zeros here. So I can basically eliminate one of the variables. So we can make 3, 0 by taking row 1 and subtracting 3, row 2 from that. And I can make row 1, row 3, I believe, yeah, row 3 minus 5, row 2. That way I can eliminate 3 and 5 in the first column. But of course, when I'm doing addition of one row to another row, or a multiple of one row to another row, I'm not really changing the solutions, because I can also reverse this process. So if I take the obtained matrix, which I'm about to write, and I just do the opposite of this operation, I will get to the original system. In other words, this process doesn't add or eliminate solutions. So let's see what we get here. So we multiply the second row by 3 and subtract from the first row. So what do we get? We get 0 here in the first row, first column. The second row multiplied by -3, we get -9 plus 2, that's -7. Second row multiplied by -3, we get 6, and then -5, that's 5. -1, that's 5. And then we get 1 here, and I'm going to put a bar here. The bar is to indicate that we know these two things are actually quite different. These things are coefficients, and these things here are in fact just constants on the other side. The second row stays the same. I'm not doing any operation in the second row. And the last row here becomes 0, so I'm multiplying the second row by -5 and add it to the last row. -15 plus 1, that's -14. And then I will multiply the second row by -5 again. So that would be 10 minus 1, that's 9. And second row multiplied by -5 plus the last row, that's -1. So this is what we get. Now, in order to keep things a little bit more organized and more clear, I would move 1 to the first row. So this is just for the purpose of making things a little bit cleaner. So we are going to swap the first and second row. So the first row becomes 1, 3, negative 2, 1. The second row and the third row are just basically what we had. So now I'm going to make use this this entry and make the last entry here 0. So if I do that, I gotta have to multiply the second row by negative 2 and add it to the third row. So I'm gonna get 1, 3, negative 2, and then 1 here. 0, negative 7, 5, 1. Those stay the same. Here is 0. This is going to be 0. I'm multiplying that by negative 2 added to that. So negative 10 plus 9, that's negative 1, and that is negative 3. Now, what I get here is a system that is much easier to solve than the original system. In fact, the system here is going to be x plus 3y minus 2z equals 1. 0x minus 7y plus 5z equals 1. 0x plus 0y minus z equals negative 3. From the last one we can get z. Z is going to be 3. We'll plug that into the second one. We get negative 7y plus 15 equals 1. So from here y becomes 2. So z is 3, y is 2. And if I plug that into the first one, I get x plus 6 minus 6 equals 1, which means x is 1. And as I said, since in every operation that we did can be reversible, this is the solution to the original system. So in other words, we have not eliminated or we have not inserted any solutions. So this is the solution to the original equation. Now, this matrix is called, I'll talk about that a little bit further, is called row echelon form. I will tell you exactly the properties that it has in details a bit later. So the key here is, if you look at these non-zero entries, everything below them are 0. And it's like a staircase here. It's always moving. If you start from the top, you're moving to the right. Your top, bottom, it moves to the right. Okay, we'll discuss that a little bit more rigorously in a few minutes. Now, starting from this matrix, you can also do more operations to make this a little bit simpler. So I'm going to start from the matrix that I had, 1, 3, negative 2, 1. Then I have 0, negative 7, 5, and 1, and then 0, 0, 3, or was it negative 1? Negative 1, negative 3. So if you look at that, you can also make these entries, these 3 entries, 0 by applying some more operations, similar operations. So the first operation that I'm going to do is I'm going to take row 1 and I'm going to add 3/7 of row 2. That way I can make that 3, 0. So if I do that, I will get 1. This becomes 0. 3/7 of negative 7 is negative 3 plus 3, that's 0. 3/7 of 5, that's 15 over 7, plus negative 2, that's 1 over 7. And then 3/7 plus 1 is 10 over 7. And then 0, negative 7, 5, and 1, 0, 0, negative 1, negative 3. Now I can use the same idea to eliminate this guy and this guy. I can do that by taking the first row, adding 1/7 of the third row, taking the second row, and adding 5 of the third row to that row. So I get 1, 0, 0. So 1/7 of negative 1 is negative 1/7, plus 1/7, that's 0. 1/7 of negative 3 is negative 3/7, plus 10 over 7, that's 1. And then 0, negative 7. Here we get 0. I'm multiplying this by 5. So negative 15, and then plus 1, that's negative 14. 0, 0, negative 1, negative 3. I can even make this simpler by rescaling these two rows. So if I multiply the second row by -1/7 and the third row by -1, I would get to 1 0 0 1 0 1 0 2 and 0 0 1 3. So as you see, these are exactly the solutions. So that would just give you x equals 1, y equals 2, z equals 3. This form is called reduced echelon form. Okay, so what are these two things? What is the echelon form and what is reduced echelon form? So notice that in this process we used 3 different operations. So now I will go over that in general. Row addition, it is adding a scalar multiple of one row to another row. So adding scalar multiples of a row to another row is called row addition. We also have row interchange. We just swap 2 of the rows. We have row scaling. We multiply one row by a non-zero. It's important that we multiply by a non-zero number. Okay, so what is the objective? The objective is to get to a matrix that satisfies these 3 properties, which are all zeros are at the very bottom. In this case, I didn't have any row that was all 0, but if I did, I would be at the very bottom. The entries below the first non-zero entry of each row are all 0. So if you look at this matrix that I got here, this is the first non-zero entry and everything below that is 0. This is the first non-zero entry of the second row and everything below that, which is this, is also 0. And the third property that is important to have is that the leading non-zero entry of each row is to the left of the leading non-zero entry of all rows below it. So it was just basically that staircase that we saw. So this one is to the left of -7, -7 is to the left of -1. With these 3 properties, we say the matrix is in echelon form. Now these row reduction and elementary, these are called elementary row operations. These 3 are called elementary row operations. With these 3 row operations, we can in fact turn every matrix into an echelon form. Now, we can even go further and do what we did on top, what we did above, which is make those non-zero entries 1 and make everything in their columns 0. So the first non-zero entry of each row is 1. In addition to what we have before, we can also make first non-zero entry of each row 1. And then these ones are the only non-zero entries in their columns. This is called reduced echelon form. Okay, so if we go back and look at what we have here, these entries here, this entry and this entry and this entry, are the only non-zero entries in their columns. And they're all 1. So I did their scaling so that I get just 1. Okay, so what's the process? In fact, there's an algorithm for getting to that. So here is the algorithm. First thing we're going to do is we interchange rows so that the first entry of the first row is non-zero. If the first column is all zeros, then you just go to the second column. And if the second column is all 0, you go to the third column. The next thing you're going to do is you use the first row and row addition to make all entries before that entry all 0. If possible, by interchanging rows, you make the second entry of the second row non-zero. If not, you move on to the next entry. And you repeat this process to obtain the echelon form. And then you scale all the rows to obtain 1s. And then you use those 1s to make everything in that column 0. So, in fact, using this process, we can get this theorem that every matrix can be turned into a matrix in reduced echelon form by applying the 3 elementary row operations. And notice that this is for every matrix. It doesn't have to be an augmented matrix. Any matrix that you take, you can just apply this process. And the proof is basically what we just talked about, which is you take your matrix, you look at the first column. If it is all 0, then you just use induction. Recursively, you can turn this one into an elementary, using elementary row operations, you can turn this one into a reduced echelon form, and then you are done. So the proof would be by induction. And if the first column is non-zero, then you swap 2 of the rows in order that, in a way that the first entry here is non-zero. Then you use that entry to get all zeros here, and then you use induction on the rest, because those operations now are not going to make any changes for this one. Or even you could just eliminate the first row first, turn that into reduced echelon form, and then use all those entries, the one leading ones, to make these possible entries here, the ones that need to be 0, turn those into 0. So the proof of this one would be by induction. Now there's also an important fact about this, which we will not really be using in this class, but I think it's an important thing and interesting thing to know, that every matrix has a unique reduced echelon form. So furthermore, the reduced echelon form of any matrix is unique. So there aren't multiple ways of multiple reduced echelon form. Echelon form doesn't need to be unique, but reduced echelon form is unique. And the proof of this one is also not that difficult. It's a little bit more involving, but it's not that difficult. So we're going to again apply induction here. We are going to show that the first columns must be the same. Why is it that the first columns must be the same? Because if the first column of this one is all 0, but the first column of this one is 1, 0, 0, well, that would be problematic, because if you look at this, let's say you start from a matrix A and you get to B and C. Both of these are reduced echelon form for matrix A. Then, if you consider a system of equation with coefficients from B and constants equal to 0, the first equation for B would be 0 times x1 plus etc. equals 0. But the first equation for C would be x1 plus etc. So if you look at this, and everything else is also 0x1. For B and C, we have 0x1 in everything except for the first one. So now, if you look at the system for B, the system for B has a solution 1, 0, 0, 0, 0. This is a solution for B, but not for C. So what does that mean? It means if you replace x1 by 1 and everything else by 0, it checks the first one, but it doesn't check the first one here, because if you replace this one by 1 and everything else 0, the first one becomes 1, not 0. So which means B cannot be a reduced echelon form for C. So these two cannot be the reduced echelon form for the same system, because we started from a system for A and we got two different things. The solutions, as we discussed, must be the same, but one of them has a solution that is not a solution to the other one. So that's a contradiction. So that's one thing to keep in mind. So the first columns must be the same. Now I'm going to show that the first rows must also be the same. So the first one is 1 here, and the first one is also 1 here. If they're both 0, then you can just look at the rest of them. You can just look at the rest of the matrix and work with those. But if the first one is all 1, is both 1, then you can look at the first equation again. If the first equation is, let's say you have 1 here, and then 2 here, and then 3 here, but you have 5 here, and then 4 here, and then everything else is 0. I'm just going to write it down as just an illustration. The first equation would be x1 plus 2x2 plus 3x3 equals 0. But here, the first equation would be x1 plus 5x2 plus 4x3 equals 0. And notice that since 2 and 3 are non-zero, everything below them must be 0, because it's in the reduced echelon form. You cannot have any non-zero entry below them. So you would have something like this, which would mean if I look at the system, I can look at one solution to this one, to the first one, that is not a solution to the second one. So for example, if you look at -5, 1, 1, it satisfies this guy and then replace everything else by 0. But -5, 1, 1 is not a solution for the second one. So replace everything, every variable 0 except for those 3 that have non-zero coefficients. And this could be done for any matrix. It doesn't have to be 2, 3, 5, 4. You could always find a solution to this one that is not a solution to that one. And that's a contradiction. So in other words, the reduced echelon form of every matrix is unique. Okay, so this is good. So now we get to do a very important theorem, but I'm going to show you with an example how that theorem is proved. Okay, so first a couple of definitions. The leading non-zero entries in a matrix in echelon form are called pivot entries. Each column that contains a pivot entry is called a pivot column. So for example, in the example that we had 3 pivot entries. So -7 and -1 are pivot entries of this matrix, and the first column, second column, and third column are called pivot columns. Those are important columns. A system of linear equations is called homogeneous if all the constants are 0. So if you have a11x1 plus a12x2 all the way to a1kxk equals 0, all the way to an1x1 to ankxk are all 0. If all of the constants are 0, we say it's a homogeneous linear system of equations. And if you look at a homogeneous system, there's always a trivial solution, which means if you plug in all the variables 0, you get a solution. So that clearly is always a solution. So the interesting part is, when do we have a non-trivial solution? And intuitively, you kind of can guess when we have a non-trivial solution. If you have more variables than equations, then intuitively it's kind of clear that there would have to be at least some non-trivial solution. Okay, so let me look at an example and illustrate that, and then we'll talk about why it would have to be true in general. If you look at this system of equations, you have 4 variables, x1, x2, x3, and x4, but you only have 3 equations. In that case, there would always be a non-trivial solution. Why is that so? The reason is, if we create the augmented matrix 2, -1, 3, 1, 1, -3, 0, 1, 0, 0, 1, -1, 4. And okay, if you notice, I didn't put the last column. I will put the last column, but it's actually not necessary to put the last column. Here is why. Because whatever row operation that you do, row swapping, row scaling, or row addition, the last column is always going to stay 0 because it's a homogeneous system. So if you're writing down augmented matrices for homogeneous systems, you can basically ignore the last column. In other cases, you cannot ignore the last column, but in that case, we can ignore the last column. So I'm going to actually start just ignoring the last column. But just keep in mind that this is corresponding to a homogeneous system. Okay, so if you do that, then we're going to just do the operations. So we're going to do the row operation would be, I'm going to make this guy not a 0. So row 1 minus 2 row 2. This gives us, I'm gonna ignore the last column, as I said. It gives me 0 here. So I'm multiplying the second row by -2 added to first row. So -2 times -3, that's 6, minus 1, that's 5. That is 3, and that's -1. 1, -3, 0, 1, 0, 1, -1, 4. I'm going to do a row interchange. Row 1 and row 2 are going to be interchanged. And that gives me 1, -3, 0, 1. 0, 5, 3, negative 1, 0, 1, negative 1, 4. Now I'm going to make this guy 0. I'm going to keep 1 because that's just easier. And I'm going to make this one 0, and I'm going to make this one also 0 to just get to the echelon form, reduced echelon form. So I'm going to take row 2 and then add 3 row 3, row 1, and then add 3 row 3, row 2, and then minus 5 row 3. Okay, so that gives me 1, 0. So I'm adding 3 times that, so that's negative 3. 3 times that, that's 12 plus 1, 13. 0, 0. So negative 5, 8, negative 21, 0, 1, negative 1, 4. Okay, now I'm going to do a row interchange just to make things a bit more clear again. Row 2 and row 3 are going to be swapped. We get 1, 0, negative 3, 13, 0, 1, negative 1, 4, 0, 0, 8, negative 21. Okay, so I'm going to do a maybe a row rescaling also, and I'm going to do 1/8 row 3. So we will change that to 1 and then negative 8, negative 21 over 8. Okay, so now we're going to do row 1 plus 3 row 3, and then we're going to do row 2 plus row 3. So we get 1, 0, 0. We add 3 times that. So that is 13 minus 63 over 8, 0, 1, 0, negative 21 over 8, plus 4, 0, 0, 1, negative 21 over 8. Okay, so this is nice because now we know the system is going to be, if I write down the system, the first one becomes x plus, so 13 over, I'm just going to write it down. Doesn't really matter what those numbers are as long as they are not 0. So I get this, or I have x1 here, and this one is x4 equals 0. The second equation would be x2 plus 4 minus 21 over 8, x4 equals 0, and the third equation is x3 minus 21 over 8, x4 equals 0. Okay, now what that means is that x1, x2, x3 can be found in terms of x4. So if you take like x4 equals 1, then you get a non-zero solution, a non-trivial solution. And what's the reason for that? The reason is we have more variables than the equations. And that brings me to the important theorem here, that any homogeneous system that has less equations than variables has a non-trivial solution. So how do we show that? It can be shown inductively. So you can start from your system, you have less equations than variables, reduce your system, and when you do reduce the augmented matrix, you can either do it inductively or even not. And as you look at the pivot entries, you have a bunch of ones, and since you have less rows than columns, there would be something that are what we call free variables. There are some things that are not pivot columns. So if you take one of those pivot columns, that variable could be completely arbitrary. So if you take that variable and set that equal to 1, then you can find all of the variables in terms of that variable. And if you do that, then you get infinitely many solutions, in fact. In other words, you have at least one non-trivial solution. So the consequence of this is every n plus 1 vectors in Rn are linearly dependent. So let's prove this one. If you have n plus 1 vectors, or even more than n plus 1 vectors in Rn, so what does that mean? Let's say the vectors are a11 all the way to a1n, n plus 1 1 all the way to an plus 1 n. So these are all in Rn. There are n plus 1 vectors. So I'm going to create a system that gives us a linear combination of these. So x1 times a11 all the way to a1n plus xn plus 1 an plus 1 1 all the way to an plus 1n equals 0 0 0. So this is true if and only if a11 x1 all the way to an plus 1 xn plus 1 is 0, and a1n x1 all the way to an plus 1 n xn plus 1 is equal to 0. Okay, so this is a system. It's linear, it's homogeneous. How many variables it has? It has n plus 1 variables. And how many equations do we have? And we have n equations. So because of that, we have n plus 1 variables, n equations. We have a non-trivial solution, which means those n plus 1 vectors are linearly dependent. And this is really important in understanding Rn and bases. So next time we'll talk about bases and how this is related to dimension of a vector space. So I will see you in the next video.